Hello, this is Professor Bailey from Dallas College. We're doing our final lecture in Chapter 2 for Elementary Statistics, which is Math 1342. This one's covering how when you're showing a graph that you created using your data, some things to stay away from or to be aware of that can make your graph misleading. It's also things for you in your reading graphs. If you see any of these things, recognize it could be someone trying to manipulate your impression of the data, etc. And so these are some things you really want to be aware of, especially now as we are inundated with data from social media, from news, etc. And if you see graphs like this, immediately a warning sign should be alerted in your mind, like, wait, is this really representative of the data they collected? And these are pretty straightforward, but they're things that you don't think about. And actually, some of these graphs I've used myself, not to be intentionally misleading, but really hadn't thought about the ramifications of the visual. Again, here are our objectives for this lecture. It's another pretty short lecture, but I'm not going to write these or go through these, but you can pause and write them in your notes or whatever you want to do. As we've seen in the last couple chapters, graphs, when properly used, are powerful forms of communication, and they're really powerful forms of thinking because it allows us to see patterns in the data that tables of numbers don't necessarily come to light as easily. However, unfortunately, when some graphs are used improperly, they can misrepresent the data and lead people to draw incorrect conclusions. We're only going to discuss a few of the most common, and specifically here is about the incorrect position of the vertical scale, incorrect sizing of graphical images, and the misleading perspective if you use three-dimensional diagrams. And this is what I've done before in building presentations. I thought, oh, this pie chart looks really cool, three-dimensional, and really didn't understand the ramifications of what other people might interpret from that pie chart. Positioning the vertical axis. The baseline of a graph is the value at which the horizontal axis intersects with the vertical axis. You can think of this as the x-axis and the y-axis, right? When we're graphing things, we have that cross. The vertical line is the y, the horizontal is the x, and where they intersect is the value of 0, okay? When a graph or plot represents how much or how many of something, it may be misleading if the baseline is not at 0, if that x-axis is not at 0. Here we have two graphs of the exact same data. Now, notice on the left, we actually have an x and y axis so that the intersection point is 0. Let me get my highlighter here. We can see that on the left graph, the intersection point is 0, but on the right graph, it's at 50. Now, it may be that, the left graph, it looks pretty stable, it looks almost uniform, but we can see that there's some slight increase after the year 2015. I assume that what the person was trying to represent in the graph to the right is the fact that, that there was what they may have considered substantial growth. In 2015, there were a little bit less than 55 million passengers at the Denver International Airport, but by 2016, this went up to close to 60,000, so an increase of about 5 million. And so what I imagine that this person did, who crafted this graph was trying to show that, I mean, we were growing at 5 million people. Here, while it's still representatively the same because the scale, you can see it, we see that it, in the overall or percentage way, it's not that big of a change. Whereas when you don't include the zero baseline, it looks like 2016 doubled the number of passengers in 2015. And this is why this is misleading, okay? And so it is possible to show this because you really want to focus on the growth, but there are ways to show this. And one way would be you could start at 50, but you'd need to have a broken line. Like 50 could be very low, but it looks like almost like a lightning bolt in a broken line that really draws people's attention to the fact that the graph is missing part of the graph. That's that lightning bolt, showing that we're not starting at zero, okay? And so this is again, this is really misrepresentative. Someone could say, well, look how much we grew. And again, most of us are visual. We're keyed in visually more than anything else, and that's just part of our human nature. Here we could say that, wow, in just 2 years, between 2015 and 17, it looks like the passenger traffic tripled and quadrupled in the next year. And so this is again, the error that's created by this image. So you have to be really careful about that vertical axis and starting it at zero, or making it really clear if you wanted to use this graph to show the changes in millions that were, more substantial changes than prior years, which almost look the same. You really want to make sure that people are aware of that. And this is just about your own integrity, as it is about them interpreting your data in the correct manner. Misrepresentation with time series. The same misleading information can be created with a time series plot. Here we have the same graphs, and again we have the same issue with the vertical axis, the vertical axes. The graph on the left starts at zero, and so you can see that there's more substantial growth in the last 3 or 4 years. But on the one on the right, again, it gives the impression that our numbers are more than double or triple or quadruple because the graph doesn't start at zero, and there's no indicator here that we didn't start at zero. And so it's just kind of a assumption that we make when we look at that graph, like, wow, it's really taking off now. We're really, numbers are increasing exponentially. I mean, that's what this looks like here. It's an exponential increase, the graph on the right. But here you can see it's just a slow growing increase. Again, as a statistician, as a data person, I can't imagine any data person who's not trying to be manipulative would want people to misinterpret their graphs and their reports. If a baseline of a bar graph or time series is not at zero, then the differences may appear to be, again, fill in the blank here, than they actually are. Again, a good place to try to hit pause and answer this and see what you think and see how well you've mastered the ideas. So hit pause, answer this question, and come back. Sorry guys, looks like a lot of my slides aren't going to have that. I've been building these slides and then coming back a couple days later to record them, not recording them immediately. Again, any of these, check your knowledge. You can look in the book, etc. But we saw that if it didn't begin at zero, it makes the changes look larger. Okay. The area principle. We often use images to compare amounts, and sometimes this is just to make our reports look cute. I remember a few years ago looking at soccer participation in the United States, and they used soccer balls to represent like how many kids were playing soccer in 10 years ago versus this year or something like that. And so the size of the ball gave an impression that the growth was much greater than it was. Okay? We often use images to compare amounts. Larger images correspond to greater amounts. To use images properly in this way, we must follow a rule known as the area principle. When amounts are compared by constructing an image for each amount, the areas of the image must be proportional to the amounts. So again, using that soccer example, if the growth had doubled, then the second soccer ball would be twice the size. The graph I'm talking about, it had the growth was maybe about 20%, and it did include the numbers, but it had a ball that was more than double. So again, the visual message to our brain is, oh wow, look how much it's grown. Even though we could see the numbers there, it was misrepresentative. Here we see something, again, the cost of a jet fuel, or this example, the area principle. The cost of jet fuel in 2016 was 0.93 cents per gallon. And in 2019, it increased to 1.78. So this is almost double, right? Or the price in 16, it was about half the price in 2019. But look at the size of the planes when we try to represent this in planes. And this is also a common mistake that someone uses. What they've done here is they've increased the width of the image and the height of the image. But remember that area is width times height. So if we increase both of those, if we double both of those, we're actually going to get an area that's 4 times as large. 2 times the width, 2 times the height, and those 2 times 2 is 4. And so that's kind of what's happening here. And so you have to be careful about that. It's a really common mistake. You think double the area, I need to make the height double and the width double. No, that doesn't work, because then you're actually making a multiple of 4. Because remember, the area of a rectangle or square is width times height. And so all these images are in rectangular form to somewhat when you're resizing them. The population of country A is twice as large as population of country B. If images are used to represent the populations, both the height and the width of the image for country A should be twice as large as the height and width of the image for country B. We just talked about this. So what do you think? Is that true or false? It's false. It's a very common mistake when I want to make the image double, to double the height and the width. But of course, again, a rectangle is height, area of a rectangle is height times width. So if we put a multiplier of 2 on both of those, we're not doubling it, we're quadrupling it. Three-dimensional graphs. Newspapers and magazines often represent three-dimensional bar graphs because they are visually impressive. Unfortunately, in order to make the tops of the bars visible, these graphs are often drawn as though the reader is looking down on them. This makes the bars look shorter than they really are. Here again, we have a couple things going on. We have that same, we have sorry, I'm misleading here. We can see that this is 2016, which has a cost of about 50 cents per gallon, and then 2019 the cost is closer to 150, so maybe 140 a gallon. And it's just hard to read these, so it can make the second graph look shorter, or etc. It also sometimes, if you do this with a pie chart, it makes the pieces of the pie which are toward the front of the 3D image look much bigger than they may be proportionally to the whole pie. Okay, again, this was a very short lecture. I should make you guys find some examples, but keep an eye out for this. If you do come across any examples, like in the newspaper, etc., take a picture of it and send it to me. I like to keep examples of this stuff, but it's also good for you, again, not even just as someone who may use statistics in your future career, but all of us need to know how to validate data. And so I think that's a very valid and powerful outcome of learning about statistics.